Hi everyone, so we're going to be looking at enthalpy change of combustion, delta HC. So it is the enthalpy change when 1 mole of the compound is completely burnt in oxygen under standard state conditions. So these are the standard state conditions. You should know these conditions. So it should be completely burnt in oxygen. So for example, enthalpy change of carbon or graphite would be the first one. So carbon reacting with oxygen, so it gives you carbon dioxide. Enthalpy change of combustion of hydrogen would be, so let's just see how we write it. So enthalpy change of combustion of hydrogen would be, so 1 mole of the compound burned completely in oxygen. So we're going to add oxygen, and H2 plus O2 will give you H2O. That's the product, right? Now we need to balance the equation to keep in mind that this one, the enthalpy change of that compound should always be 1 mole. So you cannot add any number over here. It should always be 1 here. So 2 is okay. And then this one you need to put half. And all these have to be under standard state conditions. Now for this one, so this is a substance that you're burning, so you're reacting it with oxygen. So this is going to give you, because this is an organic compound with carbon and hydrogen, so this is going to give you carbon dioxide and water. So we're going to balance the equation. There's 2 carbon here, so I put 2 here. And then there is 5 plus 1, so 6 hydrogen, so I put 3 here. And then there is 1 oxygen here and 4 oxygen here and 3 oxygen here. So that's 7 oxygen. So therefore, you need to have 6 oxygen here. So when you're balancing these kind of equations, always balance the carbon, then you balance the hydrogen, and then you balance the oxygen. Now to find enthalpy change of combustion of a substance, you need to burn it. So let's say you want to find enthalpy change of combustion of ethanol. So what you would do, we would use a spirit burner. This is a spirit burner here. And in the spirit burner, you would put the substance. So we're going to put the ethanol there, and we're going to burn the ethanol, and we'll see how much energy is released when the ethanol is burned, because this is what is enthalpy of combustion, right? So the heat produced by the combustion of the fuel is calculated from the temperature change of the water in the metal calorimeter. This container here, this is called the calorimeter. And in this, we're going to have water of a known volume, and we're going to have a thermometer to measure temperature change. If this reminds you of something, thermometer will allow you to find delta H. Water, you can get the volume of water. So from this, you can get mass of water. Sorry, this is delta T. You can get delta T from temperature. So T2 minus T1. Mass of water, you can get it from the volume of water because density of water is 1. And you also know the specific heat capacity of water. And from this, you can use the formula Q is equal to MC delta T. From the Q, you will know the amount of energy that was released by that compound. So Q will give you energy released from the compound. Now, if you know the number of moles of compound that was used, you can get delta H, which is Q divided by number of moles. So you're going to get delta H in kilojoule per mole. So this is how the delta H in this case will be enthalpy of combustion, because you're burning this compound. So here you just have to be careful about the units. So make sure you convert this to kilojoules. All right, so let's see how we apply this. So we have a question. you need to calculate the enthalpy change of combustion of ethanol from the following data. And you have to assume that all the heat from the reaction is absorbed by the water. Definitely, all the heat released by the flame is not going to be absorbed in the water. Some of it is going to be absorbed by the calorimeter, because the calorimeter also has a heat capacity. So we are ignoring this, and we are ignoring all heat loss to the surroundings. So you need to find the enthalpy change of combustion for ethanol. So mass of ethanol burnt is given, increase in water is given, mass of water in calorimeter is given. Therefore, we can find Q, mc delta T. I am going to use mass of water. Why will I use mass of water? Because I have specific heat capacity of water. I'll calculate it. I'm going to get my answer in joules. So this is joules, so I get answer in joules. I'm going to convert it to kilojoules already. And this is corresponding to the amount of energy released by 0.45 grams of ethanol. Therefore, delta H would be Q divided by number of moles. So I just need to convert this mass to number of moles of ethanol. Number of moles is mass over mol, and ethanol, this is C2H5OH. So the mol is going to be 46.07. Therefore, number of moles would be mass divided by the mol. And then delta H would be the Q in kilojoules divided by the number of moles. And this would be the delta H, so kilojoule per mole. So this one, just be careful, delta H, because it's enthalpy of combustion, this should be negative. The enthalpy of combustion from the data booklet is this value. And if you compare the value that's from the data booklet, this is more exothermic, so more heat should have been released, but our value is less than what is from theory. So this is because heat is lost to the surroundings, because you cannot eliminate the energy absorbed by the calorimeter, and you also cannot eliminate the heat loss to the surroundings, because here we are assuming that all the heat delivered by the compound is going directly into the water. This is not the case. And also these compounds, generally, they will not undergo complete combustion. There is some form of incomplete combustion that takes place here, because the flame is never completely blue. You always get a kind of yellowish, sometimes orangish tint in the flame. So this is because of incomplete combustion. You're going to try this question. So if you work this out, you should get delta H to be. So check your answer for this one.